We have another social media question coming in, and I think, Matt, you should get your sample ready. How large are the samples that have been collected, and do you expect that will be returned intact in that full size?
So this is a core sample from our test program and our test bed on Earth as we were developing our sampling system. It's roughly 2 to 2 1/3 inches long. All the core samples aren't going to look quite as intact as this one. They may break up into little chips, but this is representative of a particular rock sample. But even if it breaks up into little chips, it's still a very scientifically valuable sample, and they can still do a whole lot with it, and it's still very interesting. So you wouldn't expect all the core samples basically to look quite like this as one solid piece. But we do expect them to be about the same length of roughly about 2 inches or so.
Thank you. And that is all the time we have for questions today. I'd like to thank all our panelists for joining us. And for more information on the mission, visit nasa.gov/perseverance and mars.nasa.gov/perseverance. You can also check out the latest raw images being taken by the rover at go.nasa.gov/perseverance-raw-images. And don't forget to follow us on social media at NASA Persevere. Thanks for joining us today.
The way you and I might take a selfie is by holding a camera out with our arm and taking a single image. The way the rover takes a selfie is a little more complex than that. The way the rover takes a selfie is by using the Watson camera at the end of the robotic arm. But the Watson camera was designed to take close-up images of rocks for scientific analysis. And even with the arm fully extended, we can't cover the entire rover in a single image. To capture the entire rover, we take multiple images and then stitch them together. In order to do that, we try to hold the Watson camera sensor in the same position to take the different images. In order to keep the camera at the same position and take the different image frames, the arm may actually have to move quite a lot. It can take up to an hour of arm motion and imaging to take that entire selfie. The reason you don't see the robotic arm in the selfie is because it's moving between the different image frames that we are taking. And we include enough overlap between the images so that when we stitch them together, we don't have to include the arm. Another exciting first on the Perseverance mission is the inclusion of microphones. For the very first time, we were able to record sounds of the arm moving as it was taking the selfie. You can distinctly hear the sounds of the brakes on the arm actuators clicking open and closed. And at times, as the motors are changing speed, it almost sounds musical, like a flute. When a person takes a selfie, we just hold our arm up and take a single image. To create the first Perseverance selfie, it took an entire team of people working together for almost an entire week. In the end, it took 62 images stitched together to create the resulting selfie.
NASA's Perseverance rover has been working on its science mission with the help of the SuperCam instrument, a rock vaporizing laser and camera that examines rocks and soils. To learn more about SuperCam, we are joined by Himani Kalucha. She's the science payload uplink lead for SuperCam operations.
So SuperCam looks out of the big circular window in the white box on top of the mast, and it uses spectroscopy, which is just when light excites atoms in a rock and we get unique shifted wavelengths back to us. And so we use a combination of lasers and infrared vision, and that lets us do science even further out than the robotic arm. The lasers reach 7 meters or 23 feet away, and the infrared much, much further. And that's not even all. We have a tiny high-resolution camera and a microphone to hear Mars, and that's how we heard the helicopter.
And can you talk about some of the images SuperCam has taken and why they are important to scientists?
Absolutely. So we started by taking out images and spectra near the rover. And as you can see in this image, the laser actually blows away the dust and makes these small pits in the rocks. And that lets us analyze material that's just below the surface of the rock, which is what we care about. And then we can record the sounds of the laser with our microphone. And it tells us something about the hardness of the rocks. And then starting Sol 26, we were able to take pictures of these long distance targets like Kodiak. And that really helps the rover team understand where to drive next for more close-up analysis. And these red circles you see is actually the infrared telling us about the mineral content of these faraway outcrops. So that's how SuperCam figures out more about the geological history of Mars. And we're so excited to see what the laser can do next.
Thank you so much for joining us today, Himani. To get the latest updates, follow at NASA JPL and at NASA Persevere on social media. And on the mission website, mars.nasa.gov/perseverance, you can also find all the raw images being sent back by the rover. To get the latest updates on the rovers, we are joined by Perseverance Surface Mission Manager Jessica Samuels and Curiosity Deputy Project Scientist Abigail Freeman. Now, Jessica, Perseverance has spent the last month supporting Ingenuity helicopter operations, but now it's moving into a new phase. Can you tell us about that?
Right. So with this recent fifth helicopter flight, we're transitioning from the technology demonstration phase to more of an operations demonstration phase, as we now turn our attention more towards the robotic arm science-based portion of the mission, and as we prepare for the sample acquisition phase of the project. This past week, we completed our first close-up robotic arm science target observation by the Sherlock instrument. And as you can see here, the Watson side of that instrument was placed at different positions, getting closer and closer and closer to the surface and finishing at a mere 3.7 millimeters from the surface.
And Perseverance is preparing to collect samples from Mars to bring back to Earth. How are those preparations going?
Right. Well, in order to ensure that we are ready for this first one-of-a-kind leg of collecting samples and preparing them to bring them back to Earth, we need to ensure that we can safely place and load the robotic arm on the surface of Mars. So we first did this by loading the core drill and pushing against the rover itself, as you can see here in this image. The next day, we successfully demonstrated the capability of placing the core on the surface of Mars.
And Perseverance has been on the move. How far has the rover driven?
Perseverance has driven 345 meters so far. Over the next couple weeks, we hope to continue to check out more of our autonomous navigation capabilities and are excited about the hundreds and hundreds of meters ahead.
Thank you for that update, Jessica. Now we'll turn to Abigail. Perseverance is the new rover in town, but Curiosity is still doing science in Gale Crater. What are some of the big stories coming from Curiosity and your team?
Well, Curiosity, we're continuing to climb Mount Sharp. We just wrapped up our exploration of the Glen Torridon region, and we're now on the hunt for the zone where we know the rocks will transition from being these clay-rich rocks that formed in ancient lakes to salty rocks filled with a mineral called sulfate. We began our hunt for this clay sulfate transition at a region we informally named Mont Mercou. And we parked at the base of Mont Mercou, where erosion has cut away and made this big 20-foot high cliff. And so we drilled at the base of this cliff. We took a selfie, and we took many images of the hundreds of fine layers that we see exposed in the side of the cliff. And by analyzing these layers, we're going to understand more about the geologic processes that have shaped the area.
What is next for Curiosity?
Well, after doing a bunch of science at the base of Mont Mercou, we turned around and we ascended to the top, where we took an absolutely spectacular 360-degree color panorama of our view. And I love this image because if you look off to one side, you can see the floor of Gale Crater, where Curiosity landed. We've since climbed over 1,300 feet to get to where we are now on the side of the mound. And if you look off to the other side, you can see the terrain further ahead. Those are the hills where we know the sulfate minerals will be from our orbital data. And so that is where we're headed.
Thanks for the update, Abigail. And take a deeper dive on the mission websites, mars.nasa.gov/perseverance and visit mars.nasa.gov/MSL for the Curiosity rover. And follow at NASA Persevere and at Mars Curiosity on social media.
We went to 5 meters altitude, and then we translated out, but unlike every other flight where we gone out, we didn't come back again. This is about where we landed, and prior to that, we can see that we went to 10 meters altitude, and then came down again. So that looks great, and so we're right in the vicinity of where we wanted to be.
on another planet.
Hello, everyone, and welcome to another episode of NASA Science Live. My name is Jaree Cook, and I'm the News Events and Project Supervisor at NASA's Jet Propulsion Lab, and I'm going to be your host for today's episode. So today we're going to talk about the historic flights of NASA's Ingenuity helicopter and what they could mean for extraterrestrial flight in the future. Over the past month, NASA has been pushing the boundaries of what is possible and turning science into science facts. On April 19th, the Ingenuity Mars helicopter became the first spacecraft to achieve powered, controlled flight on another world. Since then, it has completed 4 flights that have taken this 4-pound spacecraft higher, farther, and faster than ever before. And now that the helicopter passed its technology tests, it gets to try new things that are all gravy. Ingenuity has